Okie dokie, here we go. So this is pre-calculus video for sections 1.6 and 1.7. So learning targets today are to graph transformations of parent functions, to graph piecewise functions, and write equations for functions from graphs or verbal descriptions. We're not actually going to do that in the video. That's something you're going to have to do in your homework. And also, like, given a description of the transformation, sketch the graph of that. So we're just going to start out with our parent functions and the graphs of these parent functions. If you have something like this, f of x equals c, for example, f of x equals 2, this is what we call the constant function. And the graph just looks like this. Whatever this number is, in this case 2, we just go up to where y equals 2, and it's a horizontal line. Pretty simple. Alright, we have the identity function. Identity function. This is f of x equals x. It's also our linear function, right? So linear function f of x equals mx plus b, or y minus y1 equals m times x minus x1, but just the parent function f of x equals x is the line where every x number equals the y number. So it goes through 0, 0 here, and then we have points like 1, 1, 3, 3, -4, -4. Basically, whatever the x number is, the y number is the same number. We get this line. All right, let's go to the next one. These are not as interesting as some of the others. So, more interesting functions are, the book calls this the squaring function. Squaring function. We can just call it a quadratic. The parent function here is f of x equals x squared. And let's talk about the graph of this for a little bit. So, all right, what we're doing here is I'm giving you the graphs for all the parent functions, so then you can do transformations on them. So if I have f of x equals x squared, the anchor point, or the starting point, is 0, 0. The vertex is at 0, 0. If I go 1 to the right or 1 to the left, I go up 1 from that vertex. So 1, 1, -1, 1. If I go 2 to the right or 2 to the left, I go 1, 2, 3, 4 up, because we're squaring the x number, and 2 squared is 4. We're going to have other points on here, like 3, 9. And basically, for this parent function, whatever the x number is, it's going to be x, comma, the y number is x squared. It's whatever this number is squared. So like 3, 9, 4, 16, 5, 25. All right. Let's go to the reciprocal. Actually, let's do the cubic function. We'll do reciprocal function later. Let's talk about the cubic function. So the cubic function is f of x equals x cubed. It's like the squaring function, or the quadratic, but it's cubic. So instead of an x squared, we have x to the third. So once again, if x is 0, we got 0, 0 right here. We have 1, 1. We have -1, -1. Because -1 times -1 times -1, or -1 cubed, is -1. Now if I go over to 2, I go 2 cubed. 2 times 2 is 4, times 2 again is 8, so I have 2, 8. So 2, 3, 4, 5, 6, 7, 8. So 2, 8. And then -2 would go to 2, 3, 4, 5, 6, 7, 8. -2, 8. So we get a graph that looks kind of like this, right? It's got this little S curve in there. And every point on this graph is going to be x number, comma, whatever that number is to the third power. So the x number, whatever it is, the y number is this number to the third power, right? So we can remember these important points: 0, 0, 1, 1, -1, -1, 2, 8. All right, now let's look at the reciprocal function. Right, this should all be reviewed, so if you're not taking notes, that's fine. if you're fast forwarding, if you got me on times 2 speed, that's cool too. Reciprocal function is f of x equals 1 over x. So here, this function's a little bit different. It's significantly different than the others. So here, we're dividing by whatever the input is. So if I say x is 0, I get 1 over 0, which is undefined. And that is a vertical asymptote. So here, we have a vertical asymptote at x equals 0, which is the y-axis. Now if I go to x equals 1, x equals 1, y equals 1, I get 1 comma 1. If I go to x equals 2, 1 divided by 2 is a half. If I go to x equals 3, I get a third. And basically, as I go out with my x's here, I divide by each number. So as I divide by larger and larger numbers, the outputs, the y numbers, get closer and closer to 0. Now if I do like a half here, all right, I'm going to go 1 divided by a half, which is actually 2. And as I go 1 divided by small, I get really big. So here, I've got this vertical asymptote. I also have a horizontal asymptote. Horizontal asymptote. This looks like it. At y equals 0 along the x-axis here. And I've got the point 1 comma 1. Now, if I put in negative numbers like negative 1, 1 divided by negative 1 is negative 1. So I have negative 1 comma negative 1, and I get the same behavior. As I go more and more negative, like 1 divided by, let's say 100, or negative 100 would be negative 0.01, we get closer and closer to the x-axis. Woo, but we don't go over the x-axis, right? We just have an asymptote there. And as I divide by numbers that are closer to 0, like 1 divided by negative 1/2 would be negative 2. Right? I get closer and closer, or sorry, they get more and more negative. So we get that asymptotic behavior there. All right, and the trick here, whenever we're doing shifts or translations with this, you want to translate these asymptotes, because the asymptotes here cross at 0, 0. So they make kind of a plus sign right there, 0, 0. Okay, so that is the reciprocal function. All right. Absolute value function. Let's talk about that one. Absolute value function is f of x equals absolute value of x. So if I draw my grid, or my x and y axis here, right? If I go absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. It looks like the identity function. Actually, it is the identity function for every x that's larger, or that's 0 or bigger. Now, if I go to negative 1, the absolute value of negative 1 is 1. Absolute value of negative 2 is 2. So we get this. It's a V shape with a slope of 1 on the right, a slope of negative 1 on the left, a vertex at 0, 0. Okay, that's the absolute value function. Let's talk about the square root function. That'll be our last parent function that we're going over for this lesson. All right, there are several more parent functions. This is for today. So the square root function. This is f of x equals the square root of x. Right, we start here at 0, 0. If I go 1 to the right, the square root of 1 is 1, so I go up 1, so I got 1 comma 1. If I go 2 to the right, so I'm at x equals 2, well, square root of 2 is an irrational number, and I don't want to graph irrational numbers. So you got to think, what number can I put in for x to get a nice answer? And the first nice answer is at 4. So when I'm at x equals 4, y is 2, because the square root of 4 is 2. So 4 comma 2 is on this graph. 5, 6, 7, 8, 9. We know the square root of 9 is 3. So 9 comma 3 is on the graph, and we get this curve that's basically half of a sideways parabola, half of a sideways x squared function, or x squared graph. Okay, and it's as I go to the right x, so x is my x number, the y number is the square root of whatever that number is, right, for our basic function. Okay, so in general, with any of these functions, with all of these that we just went over, except for the reciprocal function, we start at 0, 0, we go over 1, up 1, and we go over a number, and we go up whatever the function of that number is. So for example here, I go over 4, up 2, because the square root of 4 is 2. With this one, if I went over 4, I go up 4, because the absolute value of 4 is 4. If it was the squaring function, or x squared, if I go over 4, I go up 16, because 4 squared is 16. You're going to need to know how to apply that when we're looking at transformations and identifying from that vertex or that anchor point. If you go over 1 or 2, how far up do you go to identify, is it stretched or is it shrunk, that sort of thing. Later we'll talk about exponential functions and logarithmic functions, that sort of thing. Not today. All right, so we are going to do a problem where we are going to graph a piecewise function. And you're going to have several of these problems in the homework where you're graphing piecewise functions. And the reason we're doing piecewise functions is because in Algebra 2, you did a lot of work with graphing transformations of functions. So we're assuming you kind of got this under control. So we have this piecewise function here. I'm just writing it up. Minus x minus 2 squared equals greater than or equal to 1. All right, so go ahead and write that down. I'm going to draw a little grid here, and we can talk about it. And no, this will not in any way be perfect. So that's okay though. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I got a nice little grid here. We're going to go ahead and go about graphing this. So what this is saying, this piecewise function is saying, for all the x numbers less than -1, so -1 is right here. So all the ones over here, we're going off of this function here, off of this graph. So I'm going to graph 3 times the square root of x plus 10. And we need to remember, well, what does the 3 do? What transformation does that do? And what does that plus 10 do? What's that transformation? So the 3 is a vertical stretch, which means we've got that basic square root function. All the y values are tripled now. The plus 10 is going to shift our graph to the left 10. A way to remember that is to take the argument, this x plus 10, and set it equal to 0. X equals -10. Instead of starting at 0, we're starting at -10 for our number. So we're going to start with that 0, 0 anchor point now being at -10 here. It's a -10. And then what I'm going to do is I'm going to apply the same ideas as before, but where I go like over 1, I'm going to go up the square root of 1, but then I'm going to triple it because I got this stretch of 3. So I'm going to go over 1, up 1, but then multiply that by 3, and I go 1, 2, 1, 2, 3. So here we go, I have -9, 3. So right 1 from the -10 up 3. Now I'm going to go 4 to the right, because I know square root of 4 is 2. So 1, 2, 3, 4. And I usually go up 2, but it's multiplied by 3, so I'm going to go up 6. 1, 2, 3, 4, 5, 6. So here I've got -6, 6, right? Because it's 4 to the right, 6 up. And then I'm going to go 9 to the right, because I know square root of 9 is 3, so I go 9 to the right. And then I'm going to go up, I would normally go up 3, I'm going to multiply it by 3, so I'm going to go up 9. So here, I get -1, 9. But instead of putting a closed dot there, I look at this and I say there's no or equal to, so I'm going to make this an open dot. And I'm going to stop my graph there. So I'm going to sketch in my curve here. It's a stretched square root that stops at x equals -1. And we're not defined for any x's less than -10. So if I put anything less than -10 here, I'm going to get a non-real solution. I'm going to get an imaginary number. All right, so that is this part of the graph. Now I'm going to switch gears, and I'm going to graph between -1 and 1. I'm going to graph 2 times the absolute value of x minus 5. So here, absolute value of x is that V shape, right? Normally starts vertex at 0, 0, over 1 up 1 on each side, over 2 up 2 on each side, right? We got that slopes of 2 or 1 or -1. But I have a stretch by 2, right? Vertical stretch by 2, by a factor of 2, and I'm translating or shifting down 5. So I'm going to shift that vertex from 0, 0 to 1, 2, 3, 4, 5. So now I'm starting at 0, -5. Normally I'd go over 1, up 1, but because I have this 2 stretching it vertically, I'm going to multiply that distance from the vertex by 2. So I'm going to go over 1, up 2, left 1, up 2, and then I'm going to look at it and say, we got to stop for these x's because I'm only between -1 and +1. We're including the -1, so this is a solid dot right here. I'm not including the +1 because it's not including, so I'm going to do an open dot there. And basically I get this, where it's like this little V, the slope here is 2, the slope here is -2, so I went over 2, up 2, left 2, up 2, or left 2, up 1, sorry, over 1. Oh my goodness. Over 1, up 2, left 1, up 2, slope of 2, and -2. Solid dot on the -1 because it includes a -1. Open dot when x is 1 because it does not include x equals 1. All right, lastly, we're going to graph this function here. And what we can do is we can rewrite this as -x minus 2 squared plus 4. And what that's doing, right, it's our squaring function. It's normally x squared, right? Parabola starts at 0, 0, over 1 up 1, over 2 up 4, over 3 up 9, over x up x squared. But we've been shifted right to, right? Because if I take that x minus 2 and make it equal 0, we'd go +2, +2. X equals 2 is my new starting point for my vertex. But I've also gone up 4. So I'm going to put my new vertex at 2, 4. So 1, 2, 1, 2, 3, 4. So we got this point here at 2, 4. And then this negative here, being outside the function, outside after we've squared it, right there, that is a reflection in, so basically in the vertical direction, this way, over the x-axis, or in the x-axis if you haven't shifted it yet, or it's just a reflection over the, it's a vertical reflection with respect to where the vertex is. So instead of going up, I'm going to go down. So normally I would go over 1 on each side, up 1 for a squared, because 1 squared is 1. Now I'm going to go over 1, down 1. So here, over 1, down 1. So right there, over 1, down 1. Right there. So I'm at like 1, 3, and I'm at 3, 3. Now if I go over 2, I would go up 4 usually. I'm going to go over 2 and down 4. So I'm going to go 2 from the vertex, and I'm going to go down 4. So right there. Normally I would go 2 to the left and down 4 here, but we're only talking about x is greater than or equal to 1, so I'm just going to keep this solid dot on 1. Okay, I can do one more point. If I go 3 away from the vertex, normally I go up 9 because of this reflection here. I'm going to go down 9. So I'm going to go from 4, I'm going to go down 9 to get me down to -5, and 3 to the right would be about here. Something like that at 5, -5. So from here to here, I've gone right 3, and I've gone down 9. And I'm just going to sketch in my curve like that. And now we can look at this, And we say this is the graph of this piecewise function. For all the x's that are less than -1, we get this square root curve between -10 and -1. Nothing past -10 because it's not defined there. Right? In the middle, -1 to 1 for our x's, we get this absolute value function. It's been shifted down 5, and it's got a slope of 2 and -2. It's been stretched vertically by a factor of 2. And then here, for all the x's greater than or equal to 1, we get this squaring, or we get this parabola, this x squared function. Remember the parent function of x squared? So it's a parabola that's been reflected vertically, so over the x-axis. It's been shifted up 4 and right 2. So we've got this vertex of 2, 4, and it's got the same distance from the vertex as it would normally, but it's been reflected. Okay, so that's graphing a piecewise function. Hopefully that made some sense. So what we're going to do now is I'm going to put a couple of functions up on the board. I want you to sketch the graph, describe the transformations, state what the parent function is, and then use function notation to write this function in terms of its parent function. And we're going to go over it, but try to do as much as you can before I show you how to do it. All right, so we've got first one, g of x equals 3 times x plus 1 squared minus 2. The next one is g of x equals 2 times the square root of -x plus 3 plus 1. All right. So go ahead and think about what's the parent function for each of these? What are the transformations from that parent function to each of these? Sketch the graph, and then we'll talk about how to use function notation to write g in terms of the parent function f. All right, so go ahead and pause it, think about that stuff, and we'll go. All right, so parent function here, we'll write it like this. The parent function is f of x equals x squared. All right, and then we're going to list the transformations. In general, we want to list the transformations using the order of operations. Well, kind of, not really. Sorry, I misspoke. Order of operations would say do parentheses first. That's not what we want to do. What we want to do is we talk about stretches and reflections first, and then the shifts or translations. So we're going to say, are there any stretches or reflections? Yes, there's a stretch. So we have a stretch, vertical stretch, by a factor of 3. You could also say vertical dilation by a factor of 3. That would work. Right? There's nothing affecting the x multiplication-wise on the inside of the function, on that x plus 1. So that's it for our stretches. And then we're going to say, well, the -2, what does the -2 do? It is a shift or a translation down 2 units. And then this plus 1, what's that going to do? In order to see that, we can take the x plus 1, whatever's the argument of the function inside of it, set it equal to 0. Say instead of starting at x equals 0, we're going to start at x equals -1. So instead of being at 0, we're at -1. What's that transformation? It's going left 1. So it's also been shifted left 1 unit. So now we can go ahead and we can graph this fairly easily, actually. So we know we're going to have to be down 2 and left 1. So I can make my grid like this. So left 1, -1, -2 there. Actually, I'm going to do this. -2, -4. So we have a point right here at -1, -2. That's our vertex. And then we've got to apply 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 29's up there. We got to apply this vertical stretch by a factor of 3. So what we're going to do is we're going to start at that vertex. this anchor point, -1, -2, and I'm going to go to the right or left 1 unit. Normally we'd go up 1 unit because it's stretched by a factor of 3 in the vertical direction. We're going to go up 3 units. So I'm going to go right 1, I'm going to go up 1, 2, 3, and then I'm going to put a point there, 0, 1. I'm going to go left 1, up 3, -2, 1. And now if I go right or left 2, normally I would go up 4 from the vertex because 2 squared is 4 and the parent function is x squared. But I'm stretching it by a factor of 3, so that 4 gets tripled and turns into an up 12. So once again, starting at this vertex, the vertex is at -1, -2. I'm going to go right 2. So I'm going to go 1, 2 to the right, and I'm going to go up 12, which is going to put me all the way up at +10 right here. And if I go left 2 to -3, I'm still going to be at +10. So like -3, 10, 1, 10. Right, if I go right or left 3, normally I go up 9. That's right or left 3, you go up 9, because 3 squared is 9. We're going to triple that 9, and we're going to go up 27. So -2 plus 27 will put me at 25. So 1, 2, 3, 4, 5. 25 is right here. So I'd go 1 more over to 2. So that's 3 away in the right, or to the right, and then up to 25. So 2, 25. And same on the other side, -4, 25. All right, now we can sketch in our curve. If this had the same, if these gaps were the same distance, as in like this is 1 on the x and this is 1 on the y, this would look like a much more stretched, vertical stretch on this graph. Because I made the y gaps really small and the x is pretty big, it still looks like a regular parabola, like a regular x squared. It should look skinnier if you have the same scale, or not same scale, yeah, same scale for x's and y's. If like each of your boxes are squares. All right, so let's talk a little bit about writing this function in terms of its parent function f. So what I want to do here is I'm trying to say, and what this is asking, so write g of x in terms of f using function notation, And this is important for when you get into calculus and further, or even if you take pre-calc in college, they'll make you do this sort of thing. So basically it's saying g of x equals this squaring function, this x squared, right? It's 3 times the square function, which is f. F of x is a square function. But instead of just having x squared, we have x plus 1 squared. So instead of an x inside the parentheses, we have an x plus 1. The x plus 1 is the argument of the function, so that goes inside the parentheses for the f. And then outside we have this minus 2. So that would be the answer here for writing g of x in terms of f. We basically replace the fact that it's squared with an f of parentheses, because the function is f of x is x squared. Okay. So let's just jump straight to this one, and we're going to say write g of x in terms of its parent function f using function notation. That's terribly written, sorry, my handwriting's not that great. But regardless, what is the parent function here? F of x equals, parent function for this is, hopefully you said, the square root function, square root of x. So what we're going to do here is we're going to say g of x equals, well, 2 times f of, the argument of this square root function is negative x plus 3. So that's what's going to go inside the parentheses. instead of just square rooting an x like we are here, we're square rooting a negative x plus 3. So negative x plus 3, and then we have this plus 1 on the outside. So that would be writing g in terms of f right here. We basically replace the square root part with the f of. All right, now let's go ahead, let's talk about the transformations, and we'll talk about graphing it. So I'll erase that graph and do it there. So the transformations. So first we're going to start with any reflections or dilations or stretch shrink. This 2 is a stretch by a factor of 2 vertical. So we have a vertical stretch by a factor of 2. Just like that factor of 3. If this number was less than 1, we call it a shrink, or you just call it a dilation. What is this negative doing to the x here? The negative is doing there is it's a reflection. Anytime you have a negative, it's a reflection. If we had a negative 2, it'd be a reflection in the x-axis. Because it's on the x, it's inside the argument of the function. It's in here. It's a reflection in the y-axis. So you can either call it a horizontal reflection, or we can call it a reflection in the y-axis. And if we haven't done any of the transformations left, right, up, or down as far as the translations, the shifts, this negative will just reflect in the y-axis. As in, like, if the y-axis is a mirror, it makes it look like the other side. All right, now let's talk about these shifts. This plus 1, easy, just up 1, hopefully. So we shift up 1. Let's talk about this though. Right here, we have this in the argument, we have negative x plus 3. In order to find out what the shift is, we want to find the starting point. Square root always starts at 0, 0. So we say negative x plus 3 equals 0. To solve this, I'm just going to add x to each side. And the starting point is x equals 3. So instead of starting at x equals 0, we started at x equals 3, which means we moved to the right 3 units. So here, it's a shift right 3 units. And you may be like, Mr. Brace, that's crazy. It's supposed to be the opposite. The reason it's working this way is because we've got this negative in front of the x. Right here, the x plus 1 made it shift left because it was a regular x. Here it's negative x plus 3. That makes it do the opposite. And the reason is, well, you can always just solve for the starting point. Or what you can do is you can factor negative x plus 3. If I factor out the negative, like I divide this by negative 1 and I divide this by negative 1, I get negative x minus 3. So really it's a minus